Welcome back to ESP training. In this example, we're going to study a multi-stage unit operation concentrating on designing an emergency chlorine scrubber. Our objectives for this session is to understand chlorine scrubbing chemistry, then to create an ESP model, then to use ESP to simulate the chlorine scrubber using 10 weight percent sodium hydroxide. We'll review the output, then we'll try the case again with 30 weight percent sodium hydroxide. This is an overall picture of what we're trying to do. We have a three-stage column which has flow control and feedback control on the top stage, where we're going to specify a total amount of chlorine to be present in the overhead. We have a 10 weight percent solution of caustic along with a waste gas being entered from below. And we'll build this later in ESP. Right now we just want to take a look at the chemistry. This is a simulation of the amount or the percentage of chlorine remaining in the overhead as a function of caustic concentration. So what we see here at the low concentration, that we have 100% of chlorine blowing through the column, and as we increase the weight of sodium hydroxide, the amount of chlorine is reduced in the overhead, hence it's absorbed. And we can see that the response becomes essentially flat in the 16, 15 weight percent region. Looking at a function of pH versus caustic, we see that it also increases with caustic. We would expect that, also becoming flat at high caustic concentrations. The reason it becomes flat is because we are forming a solid. In this graph here, we're showing that sodium bicarbonate is precipitating from the solution at high caustic concentrations. So the question is, why is the bicarbonate controlling the pH? From this slide we can see that we have the equilibrium of sodium bicarbonate dissociating to the sodium ion and the bicarbonate ion. As long as the solid is present at the high caustic loadings, this equilibrium is fixed. That means we will not see an increase of sodium ion or bicarbonate ion, because if they do increase, the equilibrium will shift to the left to form new solid. If they decrease, the equilibrium will shift to the right to dissolve the solid to maintain the equilibrium. If the bicarbonate ion is fixed and it dissociates into hydrogen ion and bicarbonate ion, the hydrogen ion essentially becomes fixed. Therefore, we've created a buffer, and this is sometimes called a solid buffer. So as long as that bicarbonate ion is fixed by the sodium bicarbonate, the hydrogen ion is fixed here as well. Let's look at the VLE equilibria for chlorine. Chlorine is absorbed from the vapor into the aqueous phase. Then chlorine reacts with water to dissociate into hydrogen ion, chloride ion, and the hypochlorous acid molecule. And hypochlorous acid also dissociates into hydrogen ion, hypochlorite ion. But again, remember, the pH is fixed by the bicarbonate ion, so the pH is fixed here. That means the hydrogen ion fixes the hypochlorous acid dissociation as well as the chlorine hydrolysis. If the chlorine hydrolysis is fixed, the amount of chlorine aqueous in solution is also fixed. Therefore, the amount of Cl2 absorbed from the vapor stream is also fixed. So this solid buffering solution is both why we can absorb chlorine by increasing the pH, which decreases the hydrogen ion concentration, but at some point the hydrogen ion concentration becomes fixed and therefore can't move at all. Now we'll go on to build the ESP model. We are now ready to build the emergency chlorine scrubber. There are several programs from which to choose. We're going to concentrate only on ESP process for this example. So we'll go ahead and select ESP process. We may have more than one process defined in this model. We're only going to select new process, and we have to give it an 8-character name. I'm going to type in the name chlorine, and you notice I'm typing it in lowercase. The program will convert this to uppercase as necessary. So we'll press the Enter key to continue. We're now brought to the main ESP window where we can define the chemistry model, build the process, run the process, and then get some output. We'll go ahead and select chemistry model. There may be multiple models here, and you are permitted to use more than one in an ESP process. Right now we're just going to select a new model. Now you can use the same name as the process or a new name, and I'm going to select CL2 just to show you I can use a different name, and I'll press enter. We're given a choice of different thermodynamic frameworks. I can use the mixed solvent framework, which is the default, or I can use the aqueous framework. We advise not to use the hydrogen ion-based mixed solvent framework. We have included it in version 7 for legacy purposes. It'll be removed in later versions. So I'm going to select the aqueous framework, and I use the space bar to toggle it. And you can see that the arrow key has moved to the aqueous framework, and I'll press enter. We allow you to use a variety of databases. These databases are supplied with the software when you receive it. You can choose any one you want, and you can rank them in order by placing numbers, as I've done here. For this example, I don't need any private databases, so I'm going to leave them all blank and press enter. I'm now going to enter my species. We can look for species in different methods. We're going to save that for a later demonstration, and we're going to type in the name of our species. I'm going to type in CL2 and then press enter. And you see that it converted to uppercase. I'm also going to put in carbon dioxide, nitrogen, and sodium hydroxide. When I'm done, I'll press enter on a blank line. I can now decide what phases I wish to include, and again, the spacebar turns them on. I want a vapor phase. I want any solid phases that might be present. I'm not going to have an organic liquid phase, and I am not going to select oxidation and reduction. So on this screen, I'm just going to press enter. I come to the first of two bypass and continue screens. Normally, I will select continue. There might be times when you need to bypass the step, especially when you're talking to technical support. But right now, we'll select continue. The program will launch another window, which is only partly visible here in this screen. You'll come to a screen that says press the enter key to continue, so I would do that. And I'm returned now to the second step of the model generation. From here, I can modify the model by including and excluding solids via the solids selection. I am not going to do any of that at this point. I can also, I'll use the escape key to go off of that. I can also add sections to the model. What I'm now going to do is to press the enter key to generate the rest of the model. And again, I press the enter key, I get a bypass and continue. Almost always we press continue here, and I will let the program go. Once again, a window will appear. For this demonstration, it's appearing slightly off screen, and that's okay. There might be some warning messages. When it stops moving, press the enter key to continue. If there were any messages, we could display them here. There were no errors, and we're done. Select exit, and we'll move on to the next part of the build. We're now ready to build the emergency chlorine scrubber. The model has been created, so now we're going to select Process Build. There are several types of blocks you can pick to build your process. The scrubbers exist under multi-stage blocks. Here we have a choice of strippers and absorbers or extractors. Since this is an absorber type process, we'll pick that icon and double click it. You'll be given the choice of using a standard column or a mass transfer column. In this example, we'll pick the standard column. This is actually one of ESP's most complicated blocks, and we'll have to modify this block extensively to make it work. We'll first start off by giving it a title, Emergency Chlorine Scrubber. That's simple enough. We're going to change the stage numbers from 10 to 3. So we'll just blank at the and make it 03. Now you notice that the other numbers haven't changed. They will in a moment. We're going to first add the name of our stream, and it's called caustic. When I press enter, I'll be given a new screen to enter. These units aren't even close to the units I want to enter, which will be in weight units. So I will select units from the white line at the top of the screen, called the action line, and I will change my units. I want my total quantity, and I'm clicking here, to be grams, and I want my composition quantity to be also be grams. Okay, temperature centigrade is correct. Pressure, I would prefer to be in atmospheres, so I'll pick atmospheres. So now I pretty much have the units I want. I'll right-click, which allows me to go back here. The temperature of the stream is 25 degrees. The pressure is 1 atmosphere. The total flow is 1,000. The water amount will be 900 grams, and the caustic will be 100 grams. This gives me a 10 weight percent solution. I will then use the F3 key. You can see the keys designated here. I'm actually pushing the F3 key to come off the screen. And you notice that the stage numbers have changed. I'll now select the waste gas stream, and I'm entering waste gas. Spelling does count here. I'll press the enter key. Now I want to enter this in mole values, and I'll go back to units. This time I'll just select the default system to be metric. I press the escape key. Oops, that didn't actually work. We'll do that again. Excuse me, metric. Press enter, then the escape key, and you can see they've changed all to moles. It's also at 25 degrees, 1 atmosphere. I'm going to leave the total flow blank for just a moment and enter in no water. It's a dry gas. The chlorine is 5.8 moles. CO2 will be 52 moles, and the nitrogen will be 58 moles. Now you notice that the water is blank here. The program is going to insist on making this a aqueous stream unless we tell it not to. And to tell it not to, we're going to use this set phase action up here. We'll click it, and we'll tell the program that it is vapor only. And you can see that it's added this tag vapor only. We now want to make the flow set here. If you leave the flow line blank, it will add up these values to the total flow if you're in moles or in mass units. Or you can pick the word normalize, which I'll do here, and click total flow. And you can see that it's added it up. I noticed I've made a mistake. That should be 58 moles. I will go back and once again select total flow and get the correct value. So you can very easily go back and change your values. I'm going to press F3 again to clean up that screen. I'm now going to specify the vapor name called overhead and the bottom stream, which is liquid, called bottoms. I'm now ready to add some parameters to this case. What I want to do is I want to adjust the amount of caustic. What I want to do is adjust the amount of caustic here by using parameters. We're going to be using the caustic flow rate to specify a total amount of chlorine in the overhead. The first thing I'll do is I'll select parameters, and that will bring up a whole list of things I have to specify. I'm first going to select pressure profile and tell the program that is an atmospheric column. It is atmospheric on the top pressure, top stage, and atmospheric on the bottom. I can press F3 to get off that. I don't need column estimates. Sometimes if the column is very difficult to converge, I may give it a guess. I do need spec and controls, however. I will click that, okay, and I will add a new specification. Now what I want is the vapor component rate from a stage. I want the total amount of chlorine on the top stage to be 10% of the original value. So it's on stage 3. The original value for chlorine was 5.8 moles, So I want 10% of that, so I'm going to specify 0.58 moles. Pressing enter, I need to tell the program what species I'm interested in, so I will highlight chlorine, then press the spacebar. That tells the program to adjust chlorine to 0.58 moles by adjusting something. I'll get there in a second. I'll press enter, and now you can tell the program what to adjust. And what I want to adjust is the feed stream flow rate, so I'll press enter and tell it it's on stage 3. And now I'm done. I select exit. I have no other things to select on this screen. I can put heat exchangers on, I can put efficiencies, and I can change the way the column operates. I don't want to do any more than that. I will then press F3 to save this. I've noticed I have a typo in my bottoms, so I'll just go ahead there, recollect it, and get rid of that slash sign, and F3 to save the block. I am now ready to run the block. So I'll select exit, and we'll be able to move on to the next step. Alright, we've finished process build. We're now ready to run the process. We call that process analysis. So we'll go ahead and select that. By default, we end up on the calculate button, or the calculate line rather. There are some things we can add to this process. We could add a recycle and restart capabilities. Since there is no recycle in this process, we can't do anything there. I also have some calculation aids which allow us to give us some supplemental output. I don't need to do any of that. I'm just going to simply click on the calculate line, and we're going to see that the screen will partially roll off to the side. I will move this around a little bit so we can see that it in fact has converged. I scroll down and we see that we're at the process output. So I'll go ahead and press enter to clear that screen, and we have the results. So let's do some quick review. Under process stream results, I can see that my individual streams. So I can take a look at caustic. We had the caustic stream is sodium hydroxide, and you can see that the pH is very high. Now, we only entered in 1,000 grams of the material of this stream, but it's now 2.6 or kilograms, 2,619 grams. So the program has adjusted it from 1,000 up almost 2.6 times to meet our target value. Here's the waste gas, and you can see that it in fact has no water in it. It's a very simple gas to look at. The overheads, this is the amount. You see the temperature in a column is risen to about 41 degrees. And there is the chlorine at essentially 0.58, which is what we specified it to be. And this is the bottoms. This is the liquid out of the bottom. The pH is about 6.6. We'll press escape to come back a few times. Now we'll look at the process block results. And there is only one block, so we'll look at the absorber. Here under column profiles, we can see the actual column profile, the temperature on the top stage and temperature on the bottom stage. If you recall, the temperature coming in was 25 degrees. So we can see that there's been some heating on the top and some cooling on the bottom. The heating on the top is probably due to heat of reaction of the caustic reacting with the acidic chlorine gas. And on the bottom we have the gas evaporating the water as it comes down. We also report the liquid rate and vapor rate on each stage. We can also get the composition. This is on mole fractions for each of the components, and you see there's quite a few of them. We do the same for the vapors. The next thing to look at is the scaling indices. This is a tendency for these solids to appear on the column. If the number is equal to 1, the solid is saturated, and you can see that all of these values are quite a bit less than 1, so we have no tendency to form solids on this column. The column probably will not foul due to solid formation. There are no exchangers, but we can see some additional parameters for the column: the density on stage, the heat capacity, and the ionic strength. There is a material balance around the column to see that it did in fact close. The total mass, we're 10 to the minus 9th relative moles, so that's a fairly small number. And there are no Murphy efficiencies, they're all equal to 1. So now we can do a quick what-if study. What if we raised the amount of caustic from 10 weight percent to 30? And we're going back to process build to do this. So we'll select process build. and the absorber. In the actual operation of this plant, there was a typo on the input sheet, and the user actually put in way too much caustic. This actually happened in the plant. So instead of running 10 weight percent, they ran 30 weight percent. So we're going to change the values to 30. All else remains the same. So I'll press F3 to update that, F3 to leave. The parameters remain exactly the same. We'll go back to process analysis. Notice that since we've run the calculation once before, that we're on a different line. We need to move up to calculate to recalculate the process, and we'll do that. And once again, it runs very quickly. When it stops moving, press enter. And we'll once again look at the streams. The overhead gas is still about 0.58, so we have met our target specification. But let's go look at the block results. And we'll start back at the top. The column efficiencies, it's much hotter now in top stage than it was before. It was 41 degrees, it's now 61 degrees. It's hard to tell anything from the compositions, but let's look at the scaling indices. What we have here is that on the top stage, stage 3, we have sodium bicarbonate with a scaling index greater than 1. That means that it's about 6 times oversaturated. So there's a high probability of forming solid sodium bicarbonate on the top of this column. You can also see that we have a high tendency to form sodium chloride. As we move down the column to the bottom of the column, you can see that the sodium bicarbonate has an 18.2. That means it's 18 times oversaturated. So there's a very high probability to form sodium bicarbonate on the bottom of this column. And this was actually seen in the plant where they produced way too much bicarbonate solids, and it actually fouled the column. So the program gives you a very fast way of looking at what is scaling and what is not. That concludes this tutorial, and we'll take a look at others in later tutorials. For additional help and support, the course example files are located at support.olisystems.com, examplefiles.html, or you can check out our support website at support.olisystems.com or email us at support@olisystems.com. Thank you.